I find it's a lot easier to understand the rotational quantities, quantities associated with rotational motion if we compare them to the quantities associated with translational motion. Because the translational motion, I think, is a lot more intuitive. It's often a lot easier to understand something moving through space rather than something spinning around its own axis, just in terms of intuition and everyday experiences. For translational motion, for instance, the core of translational motion is, as an object is translationally moving, what about it is changing? What property is changing as an object moves through space?
Its position?
Yeah, it's changing its position. Translational motion is all about changing position. And we usually refer to that, sometimes we refer to that as X if we're just talking about motion horizontally, or sometimes as Y if we're talking about just motion vertically, or Z, depending on if we're looking at 2 or 3 dimensions. But more generally, we're often going to refer to that as R. R in the sense of radial distance. So let's say R is the position, R is how far the object has traveled. And strictly speaking, that's a vector because we're talking about where the object is. So if you've got some object that's at, let's say, this location right now, that location can be thought of as a vector, specifically the vector from where to where. Like if you wanted to describe this location as a magnitude and direction, yeah, from the origin to that location. So this is the position vector we're talking about. And in terms of practical application of this, if you wanted to describe where something is, let's say you just wanted to locate, I don't know, maybe you've got some buried treasure somewhere. You can't just say the location of this buried treasure is 5 meters. You've got to say 5 meters away from some landmark, maybe 5 meters away from the pyramid-shaped rock. And you can't just say 5 meters away from the pyramid-shaped rock. You've got to specify in which direction, maybe 5 meters to the northeast of the pyramid-shaped rock. If you want to specify a location from a landmark that people know about, you've got to describe how far it is from the landmark and in which direction. So this is why position counts as a vector. And if you're changing position, let's say you move from this old location to this new location. Then we would have our initial, your old location, and then our final would be also a vector from the origin to your new location. So here's our initial, here's our final, but how would we describe how far you actually moved? If we're talking about your position changing, how would we describe change in position mathematically? We usually write changes as delta, right? How would you actually write out delta R mathematically?
It's R final minus R initial.
Yeah, we can write this as R final minus R initial. And a delta of some vectors, you could think of that as the final plus the opposite of the initial. So we could draw our final plus, and then opposite of our initial would just be in the opposite direction. So that'd be something like this, if we add those head to tail. Or another way of drawing out subtraction of vectors that's often much more useful is to draw them from the same origin. And then ask yourself, what vector do you have to add to the initial to change it into the final? To go from initial to final, to change this location to this location, the vector you'd have to add would be this one. So this vector from initial location to final location, that is delta R. It's the vector you'd have to add to R initial to change it into R final. And this is often a very useful way of thinking about delta anything, but especially if you're dealing with vectors. That delta R is the thing you add to R initial to turn it into R final. So you start with R initial, delta R is what you add to get R final. So this would just be the displacement vector, the distance traveled. Displacement just means how far you've traveled as a vector from start to finish. And it's not necessarily the actual distance traveled. You might have taken a more meandering path to get there. You might have traveled further than that. But delta R is just the total displacement from where you started to where you finished in terms of position. Any questions on that displacement idea so far? And if you're moving, if you're changing your position as time passes, what do we call how fast you're changing your position?
Velocity.
That's velocity, yeah. So we define velocity in terms of that displacement, how much your position is changing divided by how much time it takes. So velocity is defined as delta R over delta T. How fast your position is changing. And that is a vector because R itself is a vector. So if you're moving from here to here, your velocity would be in this direction with a magnitude equal to how far you moved divided by how much time it took. And strictly speaking, that's your average velocity. You might be changing your velocity from instant to instant as you're moving around. You might not even be traveling in a straight line. So formally, we should say that velocity is the derivative of position. But that's approximately equal to the change in position over change in time. Difference being dr dt, the derivative is how fast your position is changing at that instant, whereas delta r over delta t is on average how fast your position is changing over some period of time from initial to final. And they're going to be the same value if you're moving in a straight line at constant speed, but they might be different if you're talking about changing your velocity as time passes. Any questions on the meaning of that so far? So we're defining translational velocity as the derivative of position. But what if we take it a step further and take the derivative of velocity? What would we get? What do we call how fast the velocity itself is changing?
Acceleration.
Yeah, that's acceleration. Velocity is how fast the position is changing. Acceleration is how fast the velocity itself is changing. So acceleration is the derivative of velocity. Or you can say approximately change in velocity over change in time. Measure how much the velocity changes divided by how much time passes. And that tells you the average acceleration. But the acceleration at a given instant, the instantaneous acceleration, is the derivative of velocity, how fast the velocity is changing at that instant. Also, since acceleration is the derivative of velocity, but velocity itself is a derivative, we're really taking the derivative of a derivative. And what notation do we use for the derivative of a derivative?
It's a 2 superscript.
Yeah, this is just d squared r dt squared. In other words, the second derivative. So velocity is the first derivative of position. Acceleration is the second derivative of position. So we could even write that as v equals r prime, a equals v prime equals r double prime. First derivative and second derivative of position. Which means everything you've already seen about derivatives and second derivatives from calculus applies here. If you think of position versus time as a function, let's say we're talking about just one-dimensional motion, time versus position in a single straight line, and you have some graph of position. Anything you know from calculus about derivatives applies here. Anything you can figure out about the derivative of this graph, that's really information about the velocity graph. So the derivative of position is velocity, and the second derivative of position is acceleration. So everything from calculus about how derivatives and second derivatives relate to a graph applies here. For example, it looks like we have a max at this location. also a min here, minimum here, maximum here. From calculus, what do you know about the first derivative at a max or a min? If you're trying to find a critical point, a max or a min, what do you set this derivative equal to?
Of the position graph?
Yeah, or any graph, if you want to find a max or a min, what do you set its derivative equal to?
0.
Exactly, set the derivative equal to 0, which means that at these maxes and mins, those are locations, those are times, I should say, because we're talking about time passing. Those points on the graph represent instants in time where the derivative is 0. And what's the derivative of position?
Velocity.
So that means these instants in time, this one, this one, this one, and whatever this later one is, those are the instants in time when the velocity is 0. Those are the instants when the object in motion comes to a stop briefly and turns around. So you can get information about velocity and acceleration by examining this graph with the idea of derivatives in mind. And we're going to look into that in a lot more detail later on. Later on in the quarter, we're going to look into a graph of position, graph of velocity, graph of acceleration for the same object, and compare those three graphs to figure out more information about how the object moves. Any other questions about position, velocity, acceleration so far? Then let's take a look at the corresponding quantities for rotational motion. Because for rotational motion, we can define almost the exact same ideas. The main difference is if an object is rotating, like an object that's moving through space is changing its position as time passes. An object that's rotating isn't necessarily changing its position, but what is changing that makes us call this rotation?
Direction?
Yeah, the direction. As it rotates, if you just choose one part of the object and associate a direction with it, as it rotates, that direction is changing. And how would you describe that change in direction numerically?
So with like sine or some sort of trigonometry?
Trigonometry might be useful later on for figuring out how these relate to each other. But if you're just talking about an object that's rotating, how would you describe how much its direction has changed? Like if they were just going from here to here, how much of a change in direction is that? Or what sort of units of
theta?
Yeah, theta. We're talking about an angle, right? If you're just talking about rotating an object, you can describe that rotation in terms of how far the object has rotated as an angle, presumably in degrees or radians. So the important quantity that's changing for rotational motion is not position, but angle, which we usually write as theta. And then we can define very similar concepts. Instead of velocity, how fast position is changing, we're going to be describing a quantity called angular velocity or rotational velocity. That's usually written as the Greek letter omega, lowercase omega. And in the same way that translational velocity is defined as how fast the position is changing as time passes, angular velocity is defined as how fast the angle is changing as time passes. So angular velocity means the angle, the orientation of the object is changing as time passes. It's rotating. And the amount of angular velocity is how much the angle changes divided by how much time it takes. So if you can rotate 90 degrees in 3 seconds, 90 degrees worth of change divided by 3 seconds, your angular velocity is 30 degrees per second. So that's just how far you rotate in terms of angle divided by how much time it takes. And we're going to be sometimes using degrees for this, but most of the time we're going to be using radians instead. So radians is typically what we're going to be using here, which means that the units of theta are actually unitless. Radians is technically a unitless quantity. It's defined in terms of a ratio. Radian measure is defined in terms of a ratio. The way radians is actually defined is if you take a circle of any radius, and you cut out an angle from that circle, just cut an angular pi slice wedge. Let's call this angle theta. Then that angle, that wedge, will also cut out an arc. length from this circle. We usually call that S as the arc length. The way we actually define radian measure in the first place is as the ratio of the arc length as a fraction of the radius. The definition of radian measure of an angle is angle equals the ratio of arc length over radius of the circle. And the reason we have to divide that by radius is if you make this circle bigger, let's say you keep the angle exactly the same. If you make the circle bigger, the arc length is going to get bigger. But so is the radius. But this ratio, arc length over radius, is going to be consistent. So if you have an angle that makes the arc length equal to, let's say, a third of the radius, then that means the angle is going to be 1/3 in radian measure. We just say theta equals 1/3. And there's no units there because S is measured in meters, R is also measured in meters, so the meters cancel out. One other example of this, let's say we have an angle that's so big that it's 1 full revolution. If you're talking about 1 full revolution, how much arc length, how much distance are we covering around the circle?
(360 degrees? Or the arc length?
An angle. What would be the actual distance around the circle if we go all the way around?
2 pi r?
Yeah, that's just 2 pi r. The general formula for the total circumference, the total distance around the edge of the circle, 2 pi times the radius. So the arc length is just the circumference, which is 2 pi r. Which means if we wanted to calculate the angle in radians, the angle in radian measure is defined as arc length over r, arc length over radius. So that's 2 pi r, the circumference, divided by the radius. And what happens when we divide those?
It's just 2 pi.
Yeah, radius cancel out, so we get 2 pi. So this is the reason why in radian measure, 2 pi represents 1 full revolution. Because the circumference would be 2 pi r, but arc length is that divided by r, to standardize it so that it doesn't matter what the radius is. You can also think of it, since we're dividing by r, what would be the easiest value of r to divide by?
1.
Right, just 1 unit. So if you imagine you have a circle whose radius is exactly 1, and you've got some angle cutting off an arc length, the radian measure could be thought of as the arc length that would be cut off if this circle had radius exactly 1 unit. So for instance, if we say that an angle has a radian measure of theta equals 1.7, we're saying that the angle would cut off an arc length of length 1.7 if it was on a circle of radius 1. Any questions on that so far? So I think the important things to keep in mind here are what radian measure actually means. That when we say the angle is some number in radian measure, that number literally means the ratio of how much arc length it would cut off divided by the radius of the circle. And also the fact that it's unitless. Distance and distance are measured in the same units of measurement, so units cancel out, and we end up with theta being a unitless quantity. And then theta over time, that's unitless divided by seconds. So this is just going to be in units of 1 over seconds. We would often read it as radians per second, but radians is unitless. So strictly speaking, it is just 1 over seconds. Any questions on radian measure so far? And I want to note also that radian measure, because we're just defining it in terms of these quantities that are already present in the circle, radian measure is in many ways a much more natural measurement of angle than degrees. Degrees is often used just because it's what we're used to, but ultimately, like you mentioned earlier that the circle is, or the revolution is 360 degrees, but there's nothing special about the number 360. We could define one revolution as 400 degrees, Or we could define one revolution as 100 degrees or as 1 degree. It doesn't really matter what number you use there. 360 is just used by convention partly because it has a lot of easy whole number divisors. You can easily divide it by 4, by 6, by 5, by 3, by 12. And also partly because the ancient Babylonian mathematicians really liked multiples of 60. But there's nothing particularly special about 360 degrees. But radian measure actually means something. Radian measure of an angle really means the ratio of this distance over the radius of the circle. And so it fits in very nicely into a lot of formulas. Most formulas involving angles become very simple if you write them out in terms of radians. But they become much more complicated if you have to use degrees instead. Specifically, if you use degrees, most of those formulas end up with an extra times pi over 180 or times 180 over pi, essentially acting as a conversion factor. But if you have angle measured in radians, the formulas are generally much simpler. So in most cases, we're going to be assuming we're talking about radian measure unless specified otherwise. We can take this a step further though. The idea that angular velocity is the derivative of angle. So we could take this one step further, take the derivative of angular velocity. And we call that the angular acceleration, usually written as the Greek letter alpha. So angular velocity tells you how fast you're changing the direction, how fast you're rotating. Angular acceleration tells you how fast your rate of spin is changing, how fast your angular velocity changes. So for instance, if you just got an object that's spinning at a constant speed or a constant rate, it has an angular velocity but no angular acceleration. But if it's in the process of slowing down, it has angular velocity and angular acceleration. So angular acceleration means it's changing how fast it's spinning. Any questions on how these are defined in the first place? One other thing we need to consider, should we call all of these vector quantities or scalar quantities? Does direction matter here? Like if I just start spinning this, does its angular velocity have a directionality associated with it?
Yes.
Yeah, it does have a direction, right? I could spin it in the other direction. Now maybe it's spinning at the same rate, but in a different direction. Or I could even, as it's spinning, I could start tilting the axis it's rotating around. That should count as a different direction. And in fact, we defined the direction of all of these. These are all angles. These are all vectors. And we describe the direction based on the axis of rotation. If I'm spinning this like so, the axis it's rotating around is a vertical axis. So its angular velocity should be described as a vertical vector, either straight up or straight down, because that's the axis it's rotating around. And to choose one of those, straight up or straight down, what do you think we're going to be using? If
Like the right hand?
Yeah, we can use a
right hand rule.
Anytime you've got a rotational quantity and you've narrowed it down to two possible directions, in this case, up or down, because that's the axis of rotation, you'd use a right hand rule to choose one of those. And specifically what you want to do is curl the fingers of your right hand in the direction it's rotating. Like this one's rotating like this. You might describe that as counterclockwise viewed from above. So curl the fingers of your right hand in that direction. Now my thumb's pointing upwards. So we would describe this spin as an upwards angular velocity. Not because any part of it is moving upwards. Instead, upwards tells you the axis of rotation that this is rotating around, and specifies that it's rotating this way instead of this way.
And if you increase the speed of rotation, that would also be the direction of the torque?
Yes, because if let's say it's spinning slowly, if I want to make this spin more quickly, I have to apply a torque to it. And the torque I'm applying, if you stretch out your fingers in the direction of the radius and then curl fingers in the direction of the force I applied, that's also an upwards torque. So an upwards torque causes an upwards angular acceleration. In other words, it changes the angular velocity in an upwards direction. So any change to the angular velocity, in other words, any angular acceleration, is going to require a torque, with some exceptions that we'll get to later. But in general, if you just got this spinning object and you want to change its angular velocity, maybe you want to make it spin faster or spin slower, you apply a torque to it. Or if you want to change the direction, let's say I want to make this spin around this axis instead of around this axis. If I want to tilt it like this, that requires applying torque. I'm changing the angular velocity from this way to this way. So by tilting the axis of rotation, that's a significant change in the angular velocity. And you can actually feel that. If you've got something spinning, especially if it's something heavy that's spinning really fast, if you try to tilt it, you feel some pushback. This one's kind of small, so I don't really feel it unless I'm trying to tilt it really rapidly. But if you've got, if you've got several of these that you can stack on top of each other and spin all of them at once, and you try to tilt it, it is noticeable pushback. It is noticeable that it's difficult to make it tilt. You feel some pushback on your fingers. That's because you are applying torque, you're applying this effort to make it change the axis it's rotating around. And therefore make it change its angular velocity, because direction matters here. Any questions on that so far? So let's see if we can set up an analogy to Newton's second law. I think is going to be most important. First law is just going to say if you don't apply any force, you get no acceleration. Likewise, if you don't apply any torque, you get no angular acceleration. But the second law is where things really get interesting, I think. If we take a look at Newton's second law for translational motion, Newton's second law for translational motion, net force, what does the force do to an object? You apply a force to an object, you're going to make it do what? Which one of these quantities is most directly influenced by force?
Velocity.
Velocity is changed by the force. So we could say force causes a change in velocity. But what do we call that change in velocity?
Acceleration.
Right. Force causes acceleration. Force causes velocity to change at some rate. And those should be proportional. The more force you apply, the more acceleration you get. But what's the constant proportionality that links them?
Mass, I think.
Exactly. The mass. The more massive an object is, the more force it takes to get it to accelerate at a certain rate. Or to put it another way, the more massive it is, the less acceleration you get for a certain amount of force. So mass can be thought of very conveniently as sort of a difficulty level. Mass is describing how difficult it is to change the velocity of the object. More massive means it's more difficult. It takes more effort to cause this acceleration to happen. And of course, even if it's very massive, even just a little bit of force will cause some acceleration. It'll just be such a small amount that it will be difficult to even notice. But mass is very much a difficulty level here. If we try the same thing with the rotational motion, what's the rotational version of force?
Torque.
Yeah, we've got torque, which is a vector. You apply a torque to an object, you cause angular acceleration. You're causing the rate of change to translation or to rotational velocity. So torque causes a angular acceleration. Can we just use mass again here? If we try using mass, let's actually take a look at the units first. What are the units of measurement for angular acceleration going to be? We saw angular velocity was measured in 1/seconds, right? I mean, we would often read that as radians per second, but radians is unitless, so it's really just 1/seconds. And then what's time measured in?
Seconds.
So if we've got 1/seconds divided by seconds again, what do we get?
1/second squared.
Right, the seconds combined in the denominators, so we get 1/second squared. So angular acceleration is measured in 1/second squared. Again, we would usually read that as radians per second squared, but radians is unitless, so it's really just 1/second squared. As for torque, we were looking at torque earlier as radius times force times sine theta. Sine theta is unitless, so we don't have to worry about that. So what are the units of radius and force?
Radius is meters, and then force is, I mean, is it meters squared per second squared? That doesn't sound right.
Close. There's also, if you go back to this one, meters, the acceleration is meters per second squared. But what's mass measured in?
Oh, kilograms.
Yeah. So that means force is actually measured in kilogram meters per second squared, also abbreviated as newtons. So 1 Newton, the unit of force, equals 1 kilogram meter per second squared. So we could write this as meters times newtons, but let's go ahead and flesh that out as its full expanded form, kilogram meters per second squared. Because I think that's going to be more useful for comparison. Fill that in, we can combine meters and meters to get meters squared. So torque is going to be measured in kilogram meters squared per second squared. If we just have mass here, that's going to give us units of kilograms. Do these units match up on both sides of the equation?
No.
No. Kilogram meters squared per second squared is not the same as kilograms per second squared. So that means this cannot be just mass. The constant of proportionality here is not just mass. However, we can figure out what the units of measurement has to be. If we've got kilogram meters squared per second squared here, and we just got 1 over second squared so far here, what are the missing units? What do we still need here?
Well, we would need mass, and we would need R and square it, right?
Because to get the units right, we need a kilograms, and we need a meters squared. That suggests we're going to need something about mass times something about distance squared. And we call this quantity the moment of inertia, usually written as a capital I. So this is called the moment of inertia, or sometimes just abbreviated to inertia, although that means other things as well. So I usually use the full term moment of inertia. We know that this has to have units of kilogram meters squared for this equation to work. And you could think of this as also a difficulty level, in the same way that mass is the difficulty level because more mass means it takes more force to get the same acceleration. You could think of moment of inertia as the rotational difficulty level, because more moment of inertia means it takes more torque to get the same angular acceleration. In fact, the parallel here is so strong that the moment of inertia is also sometimes called the rotational mass, or angular mass. Because the moment of inertia serves the exact same role in the rotational formulas that mass does in the translational formulas. Exact same structure. In both of these cases, we've got amount of effort equals difficulty level times the rate of change that you get. So both of these equations have the exact same structure. We just have different meanings of the variables. But this parallel here is identical. Any questions on that so far? And as you noticed earlier, since this is kilogram meters squared, moment of inertia should be equal to something about a mass times something about a distance squared, presumably a radius squared. And for a simple small object, that is in fact the case. Specifically a point mass. That is, if you've got an object that's got mass, but it's so small, not the mass being small, but the amount of space being small, the volume. If this object is so compact that you can treat it as a single point, then we can call that a point mass. Examples would be things like the weight at the end of a pendulum, or if you've got mass on a string oscillating back and forth, or if you've got just like a rock on a string that you're swirling around over your head, or even something as large as like a planet in orbit around the sun. The planet isn't exactly small, but it's small compared to the other distances involved. The distance between the planet and the sun is enormous. The distance of like the radius of the planet is small by comparison. So a planet orbiting around the sun could even be treated as a point mass because its radius is small in comparison to the other distances involved. So for a point mass, just a single point object, some distance from some rotational center, the moment of inertia can be thought of as mass times radius squared. So this is the moment of inertia for a point mass. M is the mass of the object, R is the distance from the center of rotation, the pivot point. So that can be used to figure out how difficult it is to rotate. And it turns out this works not only for just a point mass, but for any object where all the mass is the same distance from the center. This formula falls apart if some of the mass is one distance from the center and some of the mass is a different distance from the center. But for any object where all the mass is the same distance from the center, then you can use this formula, mass times radius squared. And what's an example of an object that's not just a single point, but where all the mass is located the same distance away from some central point? Can you think of any everyday object where all the mass is the same distance from the center, or at least almost all the mass?
Like a wheel, right?
Yeah, a wheel is a really good example, especially a wheel that's got like long spokes and then a heavy outer rim.
Like a Ferris wheel, I guess?
Yeah, Ferris wheel. Well, Ferris wheel has a lot of inner structure that's going to be pretty heavy. But something smaller, like maybe a bicycle wheel, for instance. A bicycle wheel, the spokes are pretty lightweight. So you've got these lightweight spokes. And you've got this much heavier outer rim and tire. And let's say that tire has mass M. And then R would just be the radius from the pivot point, because presumably this is going to be mounted on an axle at the center. So this axle would be the pivot point. And then R would just be the radius from the pivot point out to the edge. That means we can write the moment of inertia of this as mass times radius squared, because all the mass is at the same radius from the center. If it was like a solid disk instead, if the mass were more spread out, then we couldn't use this formula, because not all the mass is the same radius from the center. Like this, for instance, you've got mass spread out all throughout this region. So this is not going to be just mr squared. But a bicycle tire, you can treat it as almost all the mass is on the outer rim. So moment of inertia would be mass of the tire times radius squared. And that tells you the difficulty level. If this object is very massive, it's going to be difficult to get it to rotate, or difficult to change its rotation. If it's already spinning, it's going to be difficult to slow down and stop. Or if the mass is a long distance from the center, it's also going to be difficult to change its rotation. So once again, moment of inertia is really all about a level of difficulty. The more mass there is, the more difficult it is to change the rotational strength or rotational velocity. But also the further it is from the center, the further the mass is from the center, the more difficult it is to change the rotational velocity. And I think this is going to be most evident if you imagine extra weight attached to it. Like, let's say you've got some extra 1 kilogram weights that you could attach to the bicycle tire. If you want to attach these extra weights and you can attach them anywhere to the tire, let's say you want to make it really difficult to change the tire's rotation. Where would you attach those weights to make it really difficult to change the tire?
On the outside?
Yeah, if you attach weights to the outer edge, you're adding extra mass at a large radius. That increases the moment of inertia quite a lot. And that means it's going to be more difficult to get this spinning in the first place. And once it's already spinning, it's going to be more difficult to slow down and stop. And it's also going to be more difficult to tilt. While it's spinning, it's going to be more difficult to swivel the axis around. because it has a larger moment of inertia. And all of those, speeding up the rotation, slowing down the rotation, and tilting the axis, those all count as changes to angular velocity. In other words, they all count as angular acceleration. And angular acceleration requires torque to make it happen. And the more moment of inertia it is, the more torque is required to make that happen, the more difficult it is. On the other hand, if you take these exact same masses, these exact same extra weights, and you attach them closer in instead, that's extra mass at a small radius, so that's only a small increase in moment of inertia. So if you attach these same weights, the exact same 4 kilograms or whatever, close to the center, that's not going to be very difficult to rotate. You're not increasing the difficulty very much. And conceptually, you can kind of see this from the fact that if these masses are far away from the center, as this spins, they're traveling a long distance. But if you attach the same mass close to the center, that mass is hardly moving at all as the wheel rotates. So radius is important here. The level of difficulty, the moment of inertia, is not just how massive the object is, it's also how the mass is distributed, how far from the center of rotation the mass is. And for other shapes, there's other formulas. Like if you're talking about a solid disk, instead of an empty ring like this, if you actually fill in the middle, if you've got a solid disk, that's going to have a different formula for moment of inertia. Or if you've got a hollow sphere rotating around its own axis, or a solid sphere rotating around its own axis, or a rod rotating around its own center, or a rod rotating around its own end, those all use different formulas for moment of inertia. But they're all going to be something about a mass times a radius squared. In fact, they're usually just going to be some fraction times a mass times a distance squared. What the fraction is depends on how the mass is distributed, the shape of the object. Shape of the object. And you can find charts on that. I don't know, did they give you a chart of moment of inertia formulas already? Like just various objects? So you should be able to look it up on that. If you're dealing with a rotating hollow sphere, you just look up a hollow sphere on the moment of inertia chart, and it should have a formula for the moment of inertia of that object. And it should just be some fraction times a mass times a distance squared. Where those formulas come from is ultimately integrals. If you're dealing with some more complicated shape, let's say a solid disk spinning around its own center as a pivot point, what you could do is split this disk up into pieces we already know how to deal with. You could have this ring, and then you could have this ring, and this ring, and this ring. If you just slice this up into rings, the moment of inertia of each one of those rings is mr squared. So you can set up a formula for the moment of inertia for each one of those, and then we can use an integral to add together all these little tiny pieces. So typically the way that you get these formulas in the first place is by splitting the object up into smaller pieces that you already know how to deal with, setting up a formula for each one of those, and then using an integral to add them together. But the result is just another formula, and you can look up those formulas on a data table. Any other questions on that so far?
Yeah, I had a couple questions, just clarifying ones. First of all, so okay, never mind. So the angular mass and moment of inertia are equivalent terms,
yeah,
right? They mean the same thing. Okay, and then what's the green inside the circle, the bike wheel? Does that say?
Is the pivot point.
Okay.
The axis of rotation.
Okay, and then to clarify the point, if a point mass object we're saying, or the bike wheel where it's not a point mass, but like it's, I guess, uniform around it, those have the same formula?
Yeah, the important thing about the bike wheel is that all the mass is the same distance from the center.
And so even though it's technically not a point mass, they still are the same, like calculated and found the same way? Okay.
Yeah, the important thing about this formula is that you're only using one value for R. The idea is that all the mass is at just one single distance from the center. As long as that's true, then this should work.
Okay.
I think it also be symmetric.
Okay. So, and then just to clarify though, that like the fidget spinner example doesn't work because it's not equal to the points aren't equal.
If you have like this structure here all has mass. So we can't really say, we can't ignore this mass and this mass and this mass and this mass. We can't just treat it as all being one distance from the center.
Even though it's a symmetrical object.
Right, but it's not all the same distance from the center. Like
Okay.
if you split this up into little pieces, this little piece is the full, I don't know, 2 centimeters or whatever from the center. But this piece is only 1 centimeter from the center. This piece is only half a centimeter. So we don't have just one single distance we can use for everything.
Okay.
Alternatively, if we, like, let's say we cut this open and hollowed it out and then attached a whole bunch of mass to the outer edges. In that case, almost all the mass would be at the outer edges. So we could use mr squared, at least as a pretty good approximation. But if, if the mass is not all concentrated at one single distance from the center, or mostly concentrated at one single distance from the center, then this formula doesn't work.
Okay, yeah, that makes sense. Thank you. And then my last question was, when you talked about rotating the fidget spinner like in torque, where you can, you're not changing the direction that it's spinning, but you're moving it in space, kind of, or rotating it. How is that reflected?
Like this?
No, the other kind of way. Yes. How is that reflected mathematically? Like
in terms of the vectors, like let's say it's spinning this way. Right now, its angular velocity is upwards. If I tilt it like this, then its new angular velocity is to my right, I guess to your left. So that means as I'm tilting it, I'm changing the direction of the angular momentum or angular velocity. So even though I'm not changing how fast it's spinning, I'm changing the direction of the axis of rotation. And since angular velocity is a vector quantity, that means I am changing the angular velocity.
So because it's two-dimensional, I think the part maybe that's tripping me up is like when we talk about it translationally, there's only one direction it can change, but rotationally we have to worry about the direction it's spinning, and then also kind of what we're saying with like the axis, like it rotating. So are those
different? We're using the axis of rotation as the direction. That if an object is spinning like this, we're saying it's the direction of the angular velocity is upwards. Not that any part is moving upwards. Yeah.
Oh, because if it was spinning the opposite direction and we rotated it the same way, it's a different direction. Oh, okay.
Yeah. So if I'm spinning it this way, now the angular velocity is downwards. If I tilt it, the angular velocity is now to my left or to your right. That's
okay. So it's still only one metric for both. Okay, thank you.
And it can be kind of confusing at first, the idea of treating the axis of rotation as the direction of the vector. It is rather counterintuitive at first glance, but it's a very consistent system, and it turns out to be, in my opinion, the best system for describing how something is rotating. Like even if you're just doing something like, I don't know, maybe you got a picture hanging on the wall that's not even and you want to even it out. You can describe that rotation. Like if you want to tilt it this way, I would just describe that as an into the wall rotation. Again, nothing's moving in that direction. It's rotating around an axis in that direction. So it's a very, very precise way of describing the direction of a rotation. And precision is exactly what we need in this context. Any other questions on that?
Yeah, thank you. That makes a lot of sense.
All right, that's about it for today. Next time, we will take a look at how this applies to momentum and how we can define angular momentum in the same way we define translational momentum. In the meantime, take a look at that kinematics chart on math.ncheese.org. Review all those definitions, make sure you understand what those terms are talking about, and we'll look into more of that next time.